All right, what's up, guys? It's Professor B, and I'm back with another physics problem. So let's just get straight to it. It says a spring has a length of 0.273 meters when a 0.300 kilogram mass hangs from it. And another spring has a length of 0.750 meters when a 2.02 kilogram mass hangs from it. They want us to find the force constant and the unloaded length of the spring. So if they want us to find the unloaded length of the spring, that means that both springs are going to have the same initial length before the mass that's hanging onto it is let go and the spring is suspended. So for the first one, we're going to have a spring and we're going to call the initial length Li. And what did it say? Was it 0.273 meters? So when the mass is suspended from it, the string is going to stretch down to a length of 0.273 meters, which we can call L1. And the mass is 0.300 kilograms. Now, we should try to establish a coordinate system with y equals 0 at the equilibrium spot. Equilibrium spot is right here. Equilibrium meaning that all forces acting on the spring are balanced, so before we let the mass go. So it would look a little something like this, which is our x and our y. Using this coordinate system, we can write an expression for the magnitude of the spring when the mass is suspended from the spring. And like we said, that would cause it to have a total length of L1. So we would have L1 minus L initial, which would be this distance minus this distance would give us this distance right here, which is the magnitude of the spring after the mass was let go. Now, for the case that the mass stretches the spring to that total length of L1, the force exerted by the mass, the force exerted on the mass by the spring would yield the equation times K, because the mass is not touching the floor. The mass is suspended from the spring, so the spring is basically like holding on to it. So there is a force that the spring is exerting on the mass, and this force doesn't allow the mass. This is the force that allows the mass to hang. Now we need another expression for the force exerted on the mass by gravity. Using the coordinate system that we established, the direction of the force of gravity acting on the mass will be negative. So we will have, let me just change my eraser. So we will have negative m1 times gravity. So putting this all together, we'll set it equal to 0. Now, using the same thought process, we can do the same thing for mass number 2. Recall that if they want us to find the unloaded length of the spring, means that both of the springs have the same initial length. The initial length is the unloaded length of the spring. So that's Li. And that's going to be mass number 2, which weighs about 2.02 kilograms. And we're going to let this distance right here of 0, whoops, I'm going to do it in blue, 0.750 meters. We're going to let that distance be L2. Remember that this is M1. I should write that this is M1. And this is M2. So again, using the same thought process, we can write K times L2 minus L initial is equal to M2 times the gravity, and we set it equal to 0. Now we have the total lengths of both masses after the mass is suspended. So to find the force constant, K, we can just plug in and solve by elimination. So we have K times 0.273 minus L initial minus 0.300 kilograms times the force of gravity, which is 9.8. And for the second one, we'll have 0.750 meters minus L initial. They should have been a minus the mass of the second mass, which is 2.02 kilograms times the force of gravity, which is 9.8. Not necessary to write kilograms since we already know. So we can distribute, and we'll have 0.273 minus K times L initial is equal to 0.300 times 9.8. And on the bottom, we can do the same thing. Minus K times L initial is equal to 2.02 times 9.8. Solving by elimination, we can multiply the first equation times -1. And this will give us negative K times 0.273 plus K times L initial, which is equal to negative 0.300 times 9.8. Rewriting the bottom, we'd have 0.750 minus K times L initial is equal to 2.02 kilograms times the force of gravity, which is 9.8. Putting that into your calculator, you should get K times 0.477 plus 0, these cancel out, is equal to, this would be 16.856. And solving for the force constant, which is K, you would divide 16.856 divided by 0.477, and you would get 35.3 newtons per meter. 35 point, I'm going to do it to 4 6 figs, newtons per meter. Now that we found the force constant, we can plug it back into either one of these equations and solve for the unloaded length of the spring, which is L initial. So I am going to choose this bottom one right here. And plugging that in, we would have 35.3375 times 0.50 minus 35.3375 times L initial is equal to 2.02 times 9.8. Solving for the unloaded length of the spring, we would have 2.02 times 9.8 minus 35.3375 times 0.750 all over negative 35.3375. And that should give you 0.1898 meters, which is the length of the unloaded spring.